All right, we're gonna try and get 9 in one shot. It might get fuzzy in between when I switch papers, so stay with me. All right, 9 is, part A is asking for intervals of increase, decrease, and concavity. So intervals of increasing and decreasing is going to be given to us by our first derivative, and intervals of concavity is going to be given to us by our second derivative. Before we can do any of that, we have to find the domain. This is the logarithm function. So to find the domain of a logarithm, you take the argument, and you can't plug in 0, you can't plug in negatives. So the argument has to be strictly greater than 0, which means the domain of this function is all x's such that x is strictly greater than -4. Any values less than -4 we're not interested in. All right, so the derivative. The derivative of a logarithm function, although it's being plugged into something squared. So the first thing we have to do is chain rule and take the derivative of the power of 2. So the 2 pulls down. The new power on the logarithm is 1. You don't touch that. And then you need to multiply by the derivative of the inside. So we need to multiply by the derivative of the logarithm. Well, that's going to create a fraction. So I'm going to go ahead and put that in the numerator. And the derivative of a logarithm, the argument, x plus 4, goes in the denominator, along with the natural log of the base, but it's an ln, so that's just a 1. And then chain rule says then multiply by the derivative of the argument, but the derivative of the argument is just 1. So here's our derivative. Okay, critical numbers occur when the derivative is 0 and when the derivative doesn't exist. So you said both top and bottom equal to 0. The bottom is equal to 0 at -4, which is not in our domain. So we're not interested in it. The numerator, we need to solve where it's equal to 0. If you divide both sides by 2, that's equivalent to solving where is the natural log of x plus 4 equal to 0. Let's see, converting this into exponential form, the base is e, the power is 0, and it equals the argument. Anything to the 0th power is 1, so we get 1 equals x plus 4. Subtract 4 over to the other side, and our critical number is -3, which is in the domain. Okay, so doing a sign chart then for the first derivative. I'm going to stop it at -4 because the domain doesn't exist past then, and then we've got a single critical number at -3. All right, so let's see. Easiest number to plug in here is 0. So going back and plugging 0 into the derivative, we get, let's do it with a different marker. We get 2 times the natural log of 4 divided by 0 plus 4, which is a positive, divided by a positive. So we're positive here. And let's see, if you plug in -3.5, then you get the natural log. -3.5 plus 4 is natural log of 1/2, which is a negative number, over -3.5 plus 4 is a positive, so you get a negative over a positive, which is negative. So the function h is decreasing and then increasing. Okay, so let's go ahead and write that out. So we're increasing on the interval -3 to infinity, and we're decreasing on the interval -4 to -3. Increase and decrease. Okay, let's see. To find intervals of concavity, we need the second derivative. All right, this one's going to be a little bit messier. We've got x in a couple of places being held together with division, so we're going to need the quotient rule. So, So we've got low, d high. All right, so that's a 4. Yeah, that looks like a 4. I just got a spot on my screen here, sorry. Okay, so low, d high. So derivative of the high. Well, the 2 is a multiplier, so it's going to pull on through. And then we need the derivative of the natural log, which creates a fraction. In that fraction goes the argument. In the numerator goes the derivative of the argument, which is just 1. So there's low, d high, less high, d low, but the derivative of x plus 4 is just 1. And then that's over low squared. All right, cleaning this up. I'm gonna, let's see if I can shift this up without messing up the focus too much. If I do it slow enough. All right. All right, so cleaning this up, in the numerator, the x plus 4's here in that first fraction reduce each other. So we get 2 minus 2 ln of x plus 4 over x plus 4 squared. Very important, do not reduce these x plus 4's, okay? There's a couple of big reasons why. One of them is the numerator is held together by subtraction, but another big one is that this x plus 4 isn't even held to this ln by multiplication. It is the argument. It's being plugged into the logarithm, so it doesn't make any sense to reduce here. Okay, so again, we need where the second derivative is 0 or where it doesn't exist. Again, it doesn't exist at -4. But the function doesn't exist there, so we're not concerned about that. So we need where does the numerator equal 0. Okay, well, let's see. If you factor out a 2, this is the same as 1 minus ln of x plus 4. So setting that equal to 0, add the natural log over to the other side. Where does 1 equal ln of x plus 4? Convert that into exponential form. The base is e, the power is 1, and then it equals x plus 4. E to the 1 is just e. So subtract 4 over to the other side, and you get e minus 4 is x. So that's the number that goes on the sign chart for our second derivative. Again, doesn't go any less than -4, and then e minus 4. Okay, so plugging in numbers. E is a number, right, that's like about 2.7. So e minus 4 is, I actually kind of lined it up wrong here on my sign chart, but we're not graphing it. So this is like 2.7 minus 4. So it's definitely negative. So we could plug in 0 here to get what's happening on the right-hand side. All right, so if we go back to our messy looking second derivative, and plug in e minus 4. We get e minus 4 plus 4. Actually, we don't even need to plug it into the denominator because the denominator is being squared. So the denominator is always positive, no matter what. If we plug in e minus 4 up here, we get, oop, I'm a little bit low again. You know, I'll just do it. Well, I'll slide it up. Stay in focus. All right. So we get 2 minus 2 ln of e minus 4 plus 4, the minus 4 plus 4. Oh, wait, we can't plug in. Sorry. We're plugging in 0, not the critical number. Obviously, if we plug in e minus 4, we're going to get 0. That's how we found it. So plugging in 0, 2 minus 2 ln of 4. Let's see. I don't know what the ln of 4 is off of the top of my head, but I think it's a number that is bigger than 1, which means you're getting 2 minus a number that's a little bit bigger than 2. Let's see. Let's go ahead and get ourselves a decimal approximation if you're not comfortable with guesstimating that number. Yeah, that's -7.77. So that's negative, which means you plug in 0 and you get a negative. -3 is actually in between -4 and e minus 4. So if you plug in -3, you get 2 minus 2 ln of 1, which is 0. So you just get 2. So this interval is positive, which means conclusion about the concavity of the function. We are concave up from -4 to e minus 4, and we're concave down from e minus 4 to infinity. Okay, part B, this is where I'm going to shift this around and we might end up unfocusing here a little bit. Let's see. Okay, not too terrible. Part B is to go ahead then and identify local maxes and mins and inflection points, if it has any. So the local maxes and mins are going to come from the sign chart for the first derivative. If we're decreasing and then increasing, then we are going to get a local min at the x value of -3. Now when you plug -3 back into the very original function, h of -3, you get ln of -3 plus 4 squared, which is ln of 1 squared. Ln of 1 is 0. So our local min is at -3, 0. There is no local max. And then inflection points. We do have a place where we change in the domain where we change concavity. So the inflection point is at e minus 4. When we plug that into the function, we get ln of e minus 4 plus 4 squared, which is ln of e squared. Ln of e is 1, so that's just 1. So our inflection point is at e minus 4, 1.